final subject very quickly that I want to look at, but it's also related to the distance protection, is the measured voltage failure detection. Just in a couple of slides to look at that quickly. The measured voltage failure detection in CPREC 5 has got three aspects or three sub-functions shown there, 1, 2, 3 with the arrows. You have the one for the unbalanced faults, the classic fuse failure monitoring detection as it was done in the relays 2 generations back. That was the only one had. Then in CPREC 4 we introduced, in addition to the unbalanced one over here, the three-phase measured voltage failure detection, or three-phase fuse failure if you want to call it that. That is a more intricate function. And the final one at the bottom is a fairly specific, that's a switch onto a measured voltage failure detection. That would be the condition where, for example, the voltage MCB, the switch is switched off and you energize the line without any voltage. And typically, if you get under impedance protection, under impedance starting, Z smaller starting, you have some load current, the distance relay will trip immediately. But if you have some overcurrent or other starting techniques and the distance relay does not trip immediately when you energize the line without voltage, then you would get no indication. So, but this function would, with a small time delay, indicate that there is a energization without voltage. So three functions. They have got in the settings, you can see them, they can be applied here. You have some setting parameters that apply to the stages, and the one at the bottom you can switch on and off. This final one is the only one you can, when the entire function is switched on, the 1 and 2 are always active. The 3 you can individually turn on and off with an individual setting at the bottom. All right, the logic diagrams, screenshots from the manual. So I'm just going to briefly explain what is relevant here. The asymmetrical or the standard fuse failure technique is monitoring this negative sequence voltage, that U2 is a negative sequence voltage and U1 is a positive sequence voltage, and there are no settings required. Okay, it is a simple ratio. It's a fixed ratio. When the negative sequence is bigger than 40%, and we check this, and this works under all normal fuse failure conditions, it will pick up. So if you have a negative sequence voltage, then the fuse failure protection will want to pick up. Obviously, you can get negative sequence voltage during fault conditions, but in a power system, you cannot get negative sequence voltage without negative sequence current. So you can always see in the classic fuse failure or measured voltage failure detection, is always the voltage is the pickup criteria and the current is the blocking criteria. So you can see the presence of negative sequence current further down, I2, will go in and be the blocking input. So you can see the current inputs come through the bottom, and at that AND gate at the top there, all over there, it's a negated input at the bottom. It's where the current comes in and will block the fuse failure detection. Again, the settings, the only setting that you need to require is the current setting. And if you have ever done this, you apply the current threshold for the, at the bottom. If the current threshold is coordinated with the distance pickup. So when the distance relay minimum phase current for pickup should be effectively larger, not smaller than the fuse failure, but the fuse failure must always be able to pick up at the same time similar sensitivity or higher sensitivity than distance protection. So it will be able to securely block. Okay. The other setting at the bottom, which I need to mention, unfortunately, the dropout failure is also not that clear, the application, because if you now go into a fuse failure condition, then you see some time delays over here. Initially, it is a blocking, very, very fast blocking, but it could evolve into a fault. Remember, the fuse failure, maybe it is really a VT failure, but it's a primary fault on the VT and it turned into a real short circuit. Then you want to unblock and trip. So initially, it's not latched. Later on, you see there's a flip-flop. It is latched, but that's only after 10 seconds typically. If the fuse failure is there for 10 seconds, you say, okay, right now this is probably in the secondary wiring some problem and I need to latch this. Why do I need to latch it? Because it will take some hours or some time for the operator to get there to fix the problem. And in that time, the fuse failure blocking must remain on. And if you now get an external fault or some fault in the system creating negative sequence current, you cannot have it immediately resetting the fuse failure. And that's where the setting at the bottom comes in. Some users want to do this. They say, even if the fuse failure is active and has been active for 3 hours, if there's a negative sequence current, I want to immediately reset. In that case, you must set that parameter bottom there. Asymmetrical fail dropout on network fault, and you set it to yes. And then this will, as soon as there's negative sequence current, it will always reset the fuse failure. Not what I would recommend. The recommended setting is no, but that is something one must do for the application person to check. The other fuse failures I want to just do very briefly due to time. Maybe you can check the logic in the manual yourself. The three-phase failure is a delta technique. Basically, it will see a change in voltage, and it's important the voltage must change to a very small value. You have thresholds that you can set. Don't set it too sensitive. I think classically there were levels secondary voltage of 5 volt, I think set. Recommended would be a voltage of at least 15 or 20% would be a good minimum phase voltage. So because it cannot come during any weak in-feed or under conditions, because if there's any delta in the current and extremely sensitive, it will not be a fuse failure. The three-phase fuse failure can only happen if all 3 voltages jump to 0 and there is no delta in the current. That means that it is simply a secondary VT circuit failure, 3-phase. Typically, if you switch off the VT with the MCB. That's that one. And then the last one, as I said, the switch on one is the unusual one, is time delayed. So you may see this sometimes if you have a relay and you simulate the circuit breaker auxiliary contacts to be closed and there's no voltage connected. You can see the one pole open or that one pole closed condition will be true, greater than one pole closed, typically 3 pole closed is true, and you have no voltage. Okay, so at the bottom you see no voltage and 3 pole closed, this will pick up. It doesn't matter. It just means that during this breaker simulated closed condition with no voltage connected, the relay would indicate there's a failure. As soon as the voltage comes, you can see it's without any delay. As soon as there's a voltage present, it will reset this, the bottom input. So this is but if you were to energize a line without voltage, then after the set time delay, this fuse failure would pick up and tell you, look, the line has been energized, but there's no voltage. All right. That concludes that really, just with the final information of what the VT does. Obviously, the VT will detect failures of the VT circuit, basically broken conductors. It'll block the distance protection, block the directional negative sequence protection. Those are protection functions which could operate without or very short or no time delay and would be non-selective without voltage. And also the ground fault, high resistance ground fault uses direction measurement. If the VT fails, obviously it has no direction, those directional stages would be blocked. Optional settings, you can set it to also block other functions like normal directional overcurrent assist, over voltage protection or under voltage can all be optionally set to be blocked.